Good evening, everyone. As you already know, my name is Rahul Kumar. I'm a PMRV scholar in IIT Madras, and I'm delivering the lecture of engineering mechanics. And this is a week 8. And in this week, I will talk about principle of conservation of energy. So let's move to the one note. Okay, so as we already know that the principle of work energy, as we talked about in this last week. So the principle of work energy is actually useful for solving many different problems in engineering. But in many engineering applications, different type of energy we usually see. Okay, apart from the kinetic energy and work. But in such cases, in many cases, we use the principle of conservation of energy because the total energy always remains constant. So by using that theorem, we will solve some problem. Okay, so what we usually see in engineering mechanics, we usually talk about the mechanical energy. Okay, the mechanical energy. Okay, so from the conservation of so from the okay so from the conservation of mechanical energy mechanical energy, I'm using the word mechanical energy. Okay, because we will talk about only mechanics thing. Okay, so from the mechanical energy we usually see that the sum of, the total mechanical energy will remain what? Constant. Okay, so what are total mechanical energy? Like kinetic energy, potential energy, work done, and sometimes heat heat energy. Okay, so in the principle of conservation of energy, we usually talk about the sum of all those energy, and it will remain always constant. It will remain always constant. Okay, so in earlier class we saw kinetic energy, work done. Okay, but we didn't talk about potential energy. Okay, so we will see what are potential energy.
Sir, which is last energy?
What? Please repeat.
What is that
Heat energy.
last?
Heat energy.
Yeah, please repeat what you're saying. Hello.
After work, what is that energy, sir?
Yeah, this one, heat energy.
Heat energy comes under mechanical, sir.
Yeah, I'm talking about heat energy like when you use heat engines. Okay, so where there heat energy is converted into some energy like mechanical energies. Okay, work output like that. So I'm talking heat energy also comes under the losses. Okay, when block moves on a friction contained surface, then there will be heat dissipation. So I'm talking about those energies. Okay, so here some of the mechanical energy means all type of energies which comes under due to the mechanics. Okay, so that's why I'm including heat energy. Is it clear?
Yes.
Yeah. So there are many types of potential energies. Okay, uh, we will see the first kind of potential energy is elastic potential energy. Elastic potential energy. And second, gravitational potential energy. Gravitational potential energy. And third, it is electric potential energy. Electric potential energy. And four, chemical potential energy. Chemical potential energy. Since we are studying engineering mechanics, then we will only talk about elastic and gravitational potential energy. We will not talk about electric potential energy and chemical potential energy. But I am saying that in engineering applications, we usually see these four types of potential energy. Okay, so let's try to understand what are potential energy. Okay, in last class we talked about on a surface. Okay, we talked about a surface which is on horizontal plane, and there was a block, okay, which was moving from point. This is a datum from where we are measuring the vertical distance. Okay, so for so the block so this block is moving from point A1 to point A2, right? And suppose the vertical height of point A2 is y2, and in intermediate positions, suppose the block is here, and for very infinitesimal distance, suppose the block moves here. So for that, we usually see the in change in work done during this infinitesimal distance. Okay, so the vertical height is what? Dy. So we usually talked about when the work done. So this one is what? Gravitational potential energy. Gravitational potential energy. So in the last class, we talked about that when the block is moving from point A1 to A2 because of the application of gravitational pull. Okay, so we saw that the work done by the gravitational pull or work done by the gravitational force was given by what? W times y2 minus y1, right? This was the work done by this weight. Work done by this weight. Okay, so what we will write? So u1 to 2, after the simplification, we will write w y1 minus w y2, where w is the weight. Okay, so here we can see that there is a function. Here we can see that there is a function which is, suppose there is a function which is a function of y, and we can write as w times y. And here we can see that the work done by the gravitational force is nothing but the difference between these two, I mean the value of two functions from position 1 y1 to y2. And we can also clearly see that the work done from point 1 to point 2 is independent of this path. It is not depending whether which path it is passing through. It doesn't depend on the path. It only depends on the initial point and final point. Okay, so what we are seeing here, we can see that the work done by the gravity during the displacement is independent of path, right? So it only depends upon the initial and final values of w into y. So this function is called what? This function is called potential energy. Potential energy. So, and this potential energy what? With respect to force of gravity. Force of gravity. Because we saw that there are many types of potential energies, but here we are talking about the gravitational potential energy. So what we are seeing here, we are seeing that u1 to 2 is what? W, which is nothing but FGY, and here we can write as FGV. VG is called what? Potential energy. Okay, but as a function of Y. So here we can write what? VG at point 1 to VG at point 2, right? So this VG is called what? Potential energy, but with respect to force of gravity. Okay, so suppose if if Vg, here V is potential, G is the with respect to gravity, and 1 is what? For position 1 and 2 is for position 2. And suppose Vg2 is greater than Vg1. So what happens here? Here we can see that if Vg2 is greater than Vg1, then U1 to 2, I mean work done by the gravity from point 1 to 2 will be what? Negative, right? Which implies that work done from point 1 to 2 is negative. What does it mean? Which means that when block is moving up, which means that when block has increasing potential, when block has increasing potential, then work is what? Work is negative. Okay, are you getting my point? Which means that when potential is increasing, here when you can see that when potential is increasing, the work is what? Negative. On the other hand, we can see we can say that if the work of W is positive, then potential energy decreases, right? Which means that this is an important point. If work of W is positive, then potential energy decreases. Okay, so suppose suppose the block is going down. Suppose the block is going down. We saw that when block is going down, work done by the gravity will be positive, right? We in the last class we saw that when block is going down, work done by the gravity is positive. But when block is going down, the potential is what? Decreasing. Okay, so these two are complete. These two are complement to each other. Okay, so which means that potential is nothing but the indication of the capacity of work. Potential energy here is nothing but the indication of capacity of work. I mean, what is the capacity of work done by the gravity? Okay, suppose the block is moving down, 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 then work is going to increasing. Work is going to, but potential decreases. Okay, that's why I am saying that here if work of W is positive, then potential energy decreases. Okay, so this is one kind of interpretation. Now let's move to the spring potential energy. Spring potential energy. So in the last class, we saw that if there was a spring and if we are applying a force F, and if spring extended from point A1 to point A2, and suppose this length is L1 and this length is L2, then what was the work done by the spring force? What was the work done by the spring force? Spring force is what? This Fs. So work done by the spring force from position 1 to 2 is nothing but what? 1 by 2 k x1 square minus 1 by 2 k x2 square, where x is length of deformed length minus undeformed length, right? So in this case, we can see that here potential, whatever the potential here, the potential function is nothing but 1 by 2 k x square, right? So in this case, what we are seeing, u1 to 2 is what? Again, ve1 to ve2, right? And and from the same thing from the earlier discussion, we see that it is again doing the same thing. Okay, like when spring potential energy increases, which means that when L2 increases, then U12 is what? U12 decreases, which means that the work done by the spring force is decreasing. Okay, so that is the thing. So, so we can understand that we can use this concept of potential, use the concept, this might be boring, okay, but you'll understand the application. The concept of potential when forces are other than other than gravity force and elastic force. Elastic force. I'm saying that the concept of potential can be used apart from the gravity force and elastic force. But there is a condition. There is a condition we cannot use everywhere. And what are those conditions? The condition is that the concept of potential energy is only valid when work done by the force is independent of path. Work done by this force is independent of path. And that kind of forces are called conservative force. Those kind of forces are called what? Conservative force. Indeed, it can it can it can be used as long as the work of force is what? Independent of path. Independent of path. Path followed by its point of application. Its point of application. And this kind of force is called what? Conservative force. Conservative force. Can someone tell me the friction can be used as a potential energy? I mean, the work done by the frictional force can be used as a potential energy. Tell me.
No, sir.
Yes,
No. Why no?
why not, sir?
Yeah, that's what I'm asking.
Because it is not conservative. It
Why?
is always,
Why it is not conservative?
if we are going moving block from one point to another point and again bringing back, then it is not getting reversed.
Yeah, you are saying the right thing. I mean, suppose the block is moving on the friction surface, I mean the rough surface. Okay, so the losses here, I mean the friction force is nothing but the losses in energy. Okay, so work done by the friction, you can see that it is a function of distance, right? It is a function of distance, I mean mu k n, okay, and the distance, whatever distance it is covering. Okay, you can see that this x is nothing but the distance covered by the block on the rough surface. So suppose the path is like this, suppose another path is like this, then definitely the distance of this path and this path might be different. Okay, that's why the friction comes under what? Non-conservative force. Okay, so let's talk about some conservative. What are conservative forces? Conservative force. Okay, so I'm already talked about a force, a force acting on a particle, on a particle is said to be conservative if its work, that is U1 to 2, is independent of the path followed by the particle. Okay, so suppose in three-dimensional case, suppose this is x-axis, y-axis, z-axis. Okay, and the particle is moving from point A1. which has a coordinate x1, y1, z1, and there is a position B, I mean not position B, A2. There is position A2 which has a coordinate x2, y2 and z2. Okay, and particle is moving from A1 to A2 by different paths. By different paths. There is one path, there is a second path, there is a third path. Okay, so the principle of conservation of energy, or sorry, the work done by the conservative forces. Okay, so suppose force is acting on the particle. Okay, it says u1 to 2 is what? Is independent of path, but it depends on the only initial point and final point. And we already talked about that. The potential energy, potential energy nothing but the function of position. So what we will write? We will write v x2 y2 z2 minus v of x1 y1 z1. Okay, so here v of x y z are called what? Potential energy. Potential energy or potential function. Potential function. So I'm saying that suppose we have a closed path. Now I am using closed path. I mean particle is moving from point A1 and passing through this path and again reaching to point A2. I mean here A1 equal to A2. Then what we will do? What we will do here? Here we can see that the work done from point 1 to 2 must be what? 0. And this work done is nothing but what? Integral of f dot dr, right? And that must be 0. And here we can see that this path is nothing but what? Closed. So we will use this circle here. So if the work done by the conservative force, if f is a conservative force, then work done must be 0. So what we will use? The closed integral of f dot dr must be equal to 0. This is a condition number 1. Now suppose we have uh, we have 2 points. Suppose we have 2 points where the coordinate is a equal to x, y, and z, and there is another coordinate which has a coordinate x plus dx, y plus dy, and z plus dz. Then what is the work done? What is the work done? We will write, because this work done is what? Very infinitesimal, because I am using the work done during these 2 points. Okay, so what we will write? V of x comma y comma z minus v of x plus dx, y plus dy, and z plus dz. Okay, so if we write f as a fx, I cap, fy, z cap, and fz, k cap, and dr can be write dx, I cap, dy, j cap, and dz, k cap. Then what is the du? Du nothing but fx dx. Okay, fy dy plus fz dz. Here what will be the expression? Can someone tell me? Can someone tell me what will be the expression? If we subtract v as a function of x, y, z, and v x plus dx, y plus dy, and z plus dz, then what will be the resultant expression? Tell me. As you already know, if f there is fx, then if you want to know what will be the value of fx plus a, then what are the expression? Fa plus what? what x minus a divided by 1 factorial into f dash a plus x minus a raised to the power 2 divided by 2 factorial f double dash a. Okay, like that. That is called nothing but a Taylor expansion. Taylor expansion. So here we will not use second degree expression. We will only use what? Only the first degree. Okay, but here it is a multi-dimensional. So okay, so what we will write here, we will leave v x y z as it is. Okay, but at the place of vx plus dx vy plus dy, we will write v x y z. Okay, plus what? Tell me. We will first partially differentiate, right? dv by dx into what? Dx. Okay, dv by dy into dy plus dv by dz into dz, right? So this will be cancelled out. We will get fx dx plus fy dy plus fz dz equal to minus times of dv by dx plus dv by dy into dy plus dv by dz into dz. Okay, now we already know that we have just made a dot product, right? This is nothing but what? F dot dr. Can someone tell me what is this? If I want to write in the vector form, what can I write this? Tell me. Are you aware about the gradient of vector? Tell.
Yes.
Yeah, so if I want to write grad of v, then we can write dv by del v by del x I cap del v by del y j cap and del v by del z k cap. Okay, so here you can see that it is nothing but the grad of v, grad of v dot dr, right? And when you send this expression here, then you will get f vector is equal to nothing but the grad of v. Okay, so what are you looking here? We can see that if f is a conservative, if f is a conservative, then there must exist a potential, there must exist a potential v. I'm writing if f vector is conservative force, conservative force, then there there must exist a potential v, okay, such that it satisfies the equation what? This one was 1 and this one was suppose 2. Okay, satisfies the equation 2. I mean not 2, yeah, 2. Okay, so if f is a conservative force, then there must exist a potential v such that f vector is equal to what? Minus grad of v. Okay, so we can also write what? Fx equal to minus del v by del x, fy equal to minus del v by del y, and fz is equal to what? Minus del v by del z. Okay, now if I want to differentiate partially this equation with respect to y, what we will get? We will get del fx divided by del y fy is equal to what? Del v by del square v by del x del y. Okay, and again if I partially differentiate this with respect to z, then what will we get? Fx divided by z, I mean with respect to z we will get del v divided by del x del z. Similarly we will do for this also. Fy divided by fx, del fy divided by fx, we will get del 2v divided by del y del x. Okay, and we will partially differentiate fy with respect to fz. We will get del 2 by del y del z. Okay, and similarly if we do fx, we will get and del fz del y will get minus times del square v divided by del y del z. Can someone tell me, are these equations same? Can someone tell me, are these equations same? Definitely, because here right hand side are equal. Okay, so we will write fx fy must be equal to what? Fy fx. This is the condition number one. And when you equate this with this, we will get what? Del fx fz equal to del fz del fx. And there is a third condition, del fy divided by fz must be equal to del fz del fy. This is the sufficient condition to check. This is what? Sufficient condition to check the force is conservative or not. Okay, if these three equations satisfies, then certainly you can say that force is what? Conservative. Okay, let's take one example, then we will get it. Check this. Can someone tell me, is this force is conservative or not? Hello, are you guys here?
Yes.
Yeah, yeah. Here what are those? Fx equal to what? Fx is nothing but 1 by x, right? Fy is what? 1 by y.
Yes, sir. I think conservative.
Yeah, fz is what? 1 by z. When you check the condition, then you can see that del fx divided by del y is equal to 0 and del fy divided by del z is equal to 0. All those equations satisfy, which means what? This force is conservative. This force is conservative. Okay, which means if this force is conservative, then there must exist a potential V. There must exist a potential V such that Fx must be equal to minus times del V by del x. Okay, so we have to find this potential. So what we will do, what is here? 1 by x, right? Minus del V by del x. Send del x here. You will get that after integrating, you will get that V equal to minus ln x plus function of, because here it might be a what? Partial integral. Okay, partial integral, then which means that after integrating with respect to x, we will get ln x, but the constant must be what? As a function of y and z. Are you getting my point? Hello, are you getting my point? Why what I am doing here? Tell me
Sir,
honestly.
means constant is always function of another variables
Yeah,
about which we are not
I am
integrating.
saying that if you rearrange the thing, you will get del v equal to what? Minus del x divided by x, right? Okay. Now integrate it. If you integrate, you will get v equal to, this is what? Ln x. But since this is a integration, but the variable is up with respect to x. So the constant must be what? Function of y and z. Okay, that is not that might be not only a I mean independent of y and z. That must be as a function of, I mean that might be the function of y and z. You can see that if you differentiate this partially with v partially with respect to x, we will get the same expression, because we are differentiating partially with respect to x. Then for that, this function, I mean this constant, might be treated as will be treated as a what, constant. So that's why this constant will be a function of y and z. Take this as equation number 1. Similarly, if we use fy is equal to del v by del y, what is fy? 1 by y equal to minus del v by del y. After integrating, you will get that. I mean here, or you already found the v, right? So we can write minus del v by del y. We already got v, but as a function of y and z. When you partially differentiate this, then this term will become 0. And but here this will not become 0. So what will you get? Minus f del divided by del y as a function of what? Del y f y z, f y z. Now integrate this. When you integrate this del y will move here, and you will get minus f of y comma z is equal to what? Ln y. But this time this will be a function of what? This time this will function of what? It is a function of what? Not. This will be a function of what? Tell me.
X.
Yeah, x. Okay, so this is equation number 2. Now use third equation, third relation, that is what? Minus del v by del z. Okay, now put this here. When you put this here, and here what is fz? 1 by z. Put this fyz here, and after integrating you will see that this term all will become 0, but this one will survive. So what we will get? That will become what? Positive, right? That will become, because when minus when you multiply minus on these both expression, and when you put here, and after partial differentiating, you will get what? Del g by del z, right? And this g is a function of x, and when you integrate, then you will get gx is what? Tell me. I'm doing mistake here, some mistake. When you partially differentiate,
Constant is of x comma y.
that must be when you partially differentiate this, because this is a function of y and z. Okay, so when you partially differentiate with y, then this will not only x, because it is already a y, this might be x and z both. Are you getting my point? This will be x and z both. Okay, because when you partially differentiate with respect to y, this will become 0 and this will survive. Okay, that's why this will be a function of x and z both. So what will we write here? We will write x and z, then g, x and z will be minus times this. No, not minus times, this will be, I'm forgetting here. Yeah, this will be minus, this will be minus. So we'll get minus ln z, and as a function of fx, right, as a function of g hx. Okay, so we got this. Substitute all those, we will get minus ln x, okay, minus ln y, minus ln z, and this hx, right? So we will get, and this hx, we, because we already included as a function of x, then this will not be x. Okay, this will be just arbitrary constant. Okay, so we will get minus ln x y z, okay, plus what? C only, plus C only. So this is the potential. Okay, we are getting the potential. So definitely we are getting potential, because this force is a conservative, right? So let's move further. I know that you are getting bored, okay, but we cannot do anything. This is in your syllabus. Okay, so now let's move to your favorite topic, that is principle of conservation of energy, for which you are eagerly waiting. Principle of conservation of energy. Okay, so we already know that from the work energy principle, what were we studied? T1 U1 to 2, that must be equal to T2, right? And from the earlier discussion, we talked about that U12 is nothing but the V1 by minus V2 equal to T2. Okay, that is T1 plus V1 equal to T2 plus V2, which means that the sum of kinetic energy and potential energy will always remain constant. Okay, so we can understand this from here. Suppose there is a ceiling and there is a rod which is massless, and there is a bob which has a mass m, and when you release the bob from this position, and this position is what, a1, and reaches at this position, this is position a2, and I want to check that whether conservation of energy is following or not. So here what is t1? T1 is 0 because initially we are releasing from the rest. And what is V1? V1 is nothing but mgl, right? Because this height is L and we are assuming this line as a datum. So what is the potential energy? mgl. Okay. So and what is T2? When Bob reaches from this position to this position, this Bob will have a velocity square root of 2gl. So 1 by 2 m into v square. V square is nothing but 2gl. Okay. So 2 will be cancelled out. That will become mgl. And what is the potential? You can see that it already reaches at the datum. So that's why there is a no vertical height, that will become 0. So what? T1 plus V1 equal to MgL equal to T2 plus V2, which means conservation of energy is following here. Okay, so let's do one problem from the concept of conservation of energy. Let's solve this problem. Not this problem, we will do this later. Solve this problem. And sorry for the last from the last class, I talked that this LB is a unit of weight. But this kind of thing is very controversial, and I saw that for from some year, I mean at the point of time, LB was used as a weight. Okay, but from that it is now using as a mass. Okay, so LB is a unit of mass. LB is a unit of mass. Okay, so that's why I put as a G as a 32.2. It is a unit of mass. Okay, so take LB as a mass. Okay, not weight. Are you guys here? Hello.
Yes, sir.
Yeah, yeah.
Sir, undeformed length, is it 8 inch or 4 inch?
Yeah, it is already given, right? 4 inch. What is the answer? Did anyone get the answer? Okay, so let's discuss it. Okay. So in this problem, it is saying that this collar, initially this collar is at this position. Okay, but you have to be very careful that at this position also this spring is not relaxed. Okay, because you can see that the undeformed length of the string is 4 inch. Okay, undeformed length of string is 4 inch, but here the length of spring is 8 inch, which means that it is 4 inch what stretched. Okay, so at this position what is the potential elastic potential energy at this position? That is 1 by 2 kx square, right? 1 by 2 k, and here you have to take x, I mean delta x, because I already told you that x is nothing but the stretched length, I mean from the deformed to undeformed, right? So what is here? Here is unstretched length is 8 and stretched length is 8, right? 4 8, yeah. So that is 8 minus 4, and since you have to change it into feet because it is given into the inch, so you have to divide by 12 because 1 inch equal to 12 feet. Okay, 1 uh, 1 inch equal to 12 feet.
One,
Okay, yeah,
one,
that's why I have divided by 12. Yeah, tell me.
is it 1 feet equal to 12 inch?
No, no, 1 inch is smaller, feet is larger. Oh yeah, yeah, actually I've written in the reverse. 12, yeah, 1 foot equal to 12 inches. Okay, so that's why I have divided here. And what is the elastic potential energy at position 2? 1 by 2 k. Now you have to check that what is the length here. When you apply the Pythagoras theorem, then you can see that it is a square root of 64 plus 36, nothing but 10, right? So 10 minus 4 divided by 12 raised to the power 2. And what is the potential energy here? I mean gravitational potential energy. So Vg1. I'm assuming the datum at this position, at this line. So there definitely a potential energy, gravitational potential energy, which is nothing but the mgh, right? So here m is what? 20 into 9.81, or not 9.81, 32.2, 32.2 into this height. This is 6 divided by 12. And what is the gravitational potential energy at position 2? That is 0, right? Because it reaches at the datum. Now it is saying that if the collar released from position 1, determine its velocity. Okay, after it reaches at position 2, so we will write t1 t1 plus ve1 plus vg1 equal to t2 plus ve2 plus vg2, and here t1 is because it is released from the rest, that is 0, and we what is this 1 by 2, and we have to put the value of k, that is 3 into 4 divided by 12, 1 by 3, which means 1 by 9, right? Plus what? 20 into 32.2 into 1 by 2 equal to T2. That's what we have to determine, and that is 20 into V square plus VE2 is what? that is this. So 1 by 2 k is 3, and that is 6 divided by 12, 1 by 2, which means 1 by 4. Okay, plus 0. What is the answer? What is v we are getting? Tell me. What is v we are getting? I'm getting 5.61. 5, not 5.67 feet per second. So this is the velocity when this caller reaches as point 2. Okay, is there any problem? Are you guys getting the same answer? Tell me. Why you guys are not responding? Hello?
Yes, sir.
You are getting the same answer?
Not calculated, sir.
Okay, okay. Let's leave it. Okay. Now let's move to the conservative, non-conservative force. What are those? So, so what did we see? We saw that the weight of a particle, weight of a particle and force exerting by the spring can be, I mean not can be, are conservative forces, are conservative forces, conservative forces. But friction force, but friction force are not non-conservative, are non-conservative, conservative force or path dependent, or path dependent, which means that what I'm trying to say that suppose there is a block, suppose there is a block which is moving from point 1 to point 2. Okay, so suppose initially it is a, and this is rough, this surface is rough. Suppose it is a initially kinetic energy T1 plus gravitational potential energy V1. Okay, and finally it reaches at point 2, which is a kinetic energy T2 and potential energy V2. But if this surface is rough, then these two, I mean these both sides cannot be equal, because there is a losses. Okay, so because this there is a friction, then but what we will say here, the principle of conservation of energy, I mean, is false here. No, okay, because it is not false, because it says that you have to sum all those forces. Okay, you have to sum all those forces, and it will remain always same at any position, which means that if we want to equate all those energy at position 1 to 2, then we have to consider all those forces. Okay, so what we will write? For 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 non conservative force, for non-conservative forces, we have to use this equation, T1 plus V1, and suppose there is elastic potential energy also, VE1, then you have to write one more expression, which is work done by non-conservative force, okay, from position 1 to 2, and that must be equal to T2 plus Vg2 or V2, okay, V2 plus VE2, okay. So we have to use this equation for non-conservative forces, okay. So yeah, so now you can solve this problem. Is there any problem?
Sir, what is VE?
V is elastic potential energy. I'm not considering this situation where all those, I mean, block is moving under gravitational force. I'm saying that, yeah, I'm saying that suppose there is a situation, suppose the block, there is a spring attached to the block. Okay, so I'm saying for that situation. Okay,
Okay.
yeah. So now let's solve this problem. This problem is already been asked in GATE exam. You know, this problem can be easily solved using work energy theorem, but still you can apply conservation of energy. And tell me quickly what is the answer for this.
14,110.
Yeah, that is correct. Okay, so yeah, we can also apply work energy theorem, I mean conservation of energy, and also we can apply work energy theorem. Okay, but
Hello, sir.
yeah, tell me.
Sir, am I audible to you?
Yeah, yeah, you are audible now. Hello, hello. Oh my God.
Okay, I will talk to you
Yeah,
later.
hello. Yeah, hello.
Yes.
Yeah, actually there is a very internet, yeah, internet issue here. Okay. Yeah. Okay, what are you guys discussing?
I got 4.3 kilojoule, sir. I just
Uh,
took all energies.
okay, I think that is not the correct answer. That is, I think, yeah.
14,111.
Yeah, that is correct actually. Okay, so first I will apply work energy theorem, okay, and we will see we are getting the correct answer on it, because that is easy, very easy to apply. So what is that? What were that? If you apply work energy theorem, that is very simple. T1 plus U1 to 2, that is simply what? T2, right? And what is T1? T1, it is saying that the mass is currently being lowered at a velocity 2 meter per second. So you have to just write 1 by 2, 2, yeah, 2000, that is 2000 into V square, right? So that is 4. Plus, since this has a moment of inertia, which means this is a rigid body, okay, so you have to consider, and it is rotating, so you have to also consider the rotational kinetic energy. So what is that? 1 by 2 I omega square, okay. Since I have not talked about kinetic energy by the rotational motion, but definitely we will talk about later, and that is 1 by 2 I omega square, okay. So now you have to see what are other work done here, water work done here. And here you can see that the mass is brought to rest in a distance of zero point 0.5, which means that after a distance of zero point 0.5 meter, the mass is at a rest position. Okay, so definitely there will be a work done by the gravitational pull. And what is the work done? That is, since mass is getting lower, so that work done by the gravity is positive, right? So mgl, okay, that is mg, I mean 2000 into 9.81 and zero point 0.5, okay. And you have to also consider, because it is saying that work absorbed by the brake, I mean, you are applying a brake. So there is a definitely work done by the friction force. And we already know that the work done by the friction force is a what? Negative quantity, right? That is a negative quantity. So you have to write minus WF. And finally, there is no energy here. I mean, there is no kinetic energy here, because the block is, the mass is brought to rest. So you have to just substitute 0. Okay. So what is work done by the friction force? I mean, work absorbed by the brake. That is nothing but 1000. I mean, that is 4000. 4000 plus 1 by 2, that is 150, and omega is what? V by R, and that is V, I mean 2 divided by, here what is R? 1, right? Plus 2000 into 9.81 into zero point 0.5. So what is WF? You will get 150 into 2 plus 4000 plus 2000 into 9.81 into zero point 0.5. You will get 1400, I mean 14,110, or 14.11 kilojoule. So this is the answer. Are you guys getting the same? Tell me.
Yes, sir.
Yes, sir.
Yeah, okay. Now let's do one more problem, okay? And this problem is actually very good. Yeah, solve this problem. You might be thinking that this kind of problem will not be asked in GATE, but you know, GATE is getting very difficult now, year by year. Okay, so you have to be very habitual for this problem also. Okay, so do not, please, I will say, do not ignore all these problem, all these type of problems, because they're asking very out of the box questions. If you are thinking that you will solve all the previous year, then you can crack GATE exam, but this is not the thing.
Sir, how to crack something?
Yeah. I mean, for the to crack the GATE, you definitely you have to solve as much as problems. Okay, and you have to also practice problems, and I mean try gate series. Okay, gate test series. If you are not trying test series, then definitely you cannot crack. Okay, so join test series.
Okay, sir.
Yeah, you have to be very careful here. It is saying that maximum velocity of the caller is achieved when it passes through point A. Are you guys trying?
Yes, sir.
Yeah. Okay, so let's solve it. It is saying that the caller is at point C initially. Okay, and if I am assuming this line as a datum, if I am assuming this line as a datum, then at point C, what will be the potential energy? What will be the potential energy? Vg1, that is nothing but mgh, right? So what is m? 2.5, 32.2. Okay, and what is h? H is nothing but 7, right? 7 divided by 12, because it is given into the inch. Okay, now you can see that there is no kinetic energy at this position because the collar is at rest at point C. Okay, so T1 is equal to 0. Okay, is there any other energy? Yeah, so you can check that there is also spring potential energy. There might be a spring potential energy. You have to check that. You can see that when the collar reaches at this point, when the collar reaches at this point, then what is the length of this spring? It is a 3 and the radius is 7, then definitely this length is what? 4. And you can see that the spring has an undeformed length of 4, which means that spring is relaxed here. So there is no elastic potential energy here. Okay, so you have only what? Gravitational potential energy. Now you have to study at point A. So now what is Vg2? 0, right? Because the collar is at point A, and at point A is passing through the datum. That's why gravitational potential energy is 0. And what is the kinetic energy here? Suppose the velocity of collar at point A is v. So you can write 1 by 2, 2.5 divided by 32.2. I mean not 32.2, only 2.5, because yeah, 2.5 into v square. And is there any put other potential energy? Yeah, definitely it has a elastic potential energy. And when spring is at this position, then what is the length? This length is 3, this length is 7, then this length is what? 7 square plus 3 square. Okay, that is nothing but 49 plus 9 square root 0.5, that is 7.615 inch. Okay, so you have to write spring potential energy at position 2, that is 1 by 2 into k. K is not given, and yeah, so you have to subtract this from this because it is saying that undeformed length is 4. So 7.615 minus 4. Now you have to convert it into feet. Okay, that is square. So you will write what? After the approximation, this will become 2.5 by 2.5 divided by 2, that is 1.25 v square, 1.25 v square, and this will become what? 0.0454 k. Okay, yeah. So yeah, this is the thing. Now you have to equate all those. So when you equate so we will get 2.5, and that value is, this value is, yeah, 7 for 46 point. This value is 46.958 equal to 1.25 v square plus 0.0454 k. Here you can see that we have two unknowns, okay, and we have only one equation, and we have to determine the spring constant key k. But for the to determine k, we need v. So how will you determine? Tell me, how will you determine? We need one more
Sir, please
equation. Yeah,
repeat the question, sir.
I'm saying that you can see that here there are two unknowns, right? K and v.
Hmm,
Okay, and
hmm, hmm,
there is
hmm.
only one equation, and still we have to determine k. So how will you determine k? Because without the
Sir,
value
by half MB square,
half mv square, why? Means what? I'm not getting your point.
by energy conservation law, half MB square, we could get the value of V. Then after that, putting the value of V, then we could get the value of spring constant
You are saying
K.
that I have to equate this by half mv square,
Yes,
but for that half mv square, that position is which position? That is which position you are talking about? Because when you talk about this, then there is a definitely spring potential energy, because this position is not relaxed.
yes,
Okay,
sir.
and this,
Hmm,
at this position there is still kinetic energy.
hmm, hmm,
Okay, and this can, I mean, energy at this point can be equated by potential energy at this point.
hmm.
Okay, and then definitely you will have two unknowns. So what will you do
Sir,
for that? Yeah, tell me.
they have given maximum velocity. Is there
Yeah,
any?
yeah, they're saying that the maximum velocity of color is achieved as when it passes passing through A. Okay, it is saying that suppose the caller is at position A. Okay, and definitely this point is what? This point is stretched position, right? Then definitely spring force will act like this. Okay, and there is a normal reaction N. Okay, and there is a weight W, and suppose this theta is, I mean, this angle is theta. When when you are saying that the velocity is maximum at this position, when velocity will be maximum? When velocity will be maximum? When there is no net force at this point in vertical direction, right? When there is no net force in this vertical direction, I'm saying that there is no tangential energy. Okay, at not tangential acceleration at point A. Okay, that is the
Means
position
no
where
acceleration.
velocity will be maximum. Okay, because apart from this position, you can see that there might be some net force. There might be some net force. Okay, because the weight might be not balanced by the spring force. But here, when weight is balanced by this component, then there is no net force at this in this component. Then the velocity will be maximum. Then what will you write? This position is, I mean, fs sine theta. So if you need this position, for this position velocity is maximum, you have to write fy, summation of fy might be 0, right? Summation of fy must be equal to 0, that is fs sine theta minus W must be equal to 0. Here what is Fs? Fs is nothing but Kx. And what is K? K we have already given what? 2.5, right? No, not 2.5. Yeah, we have to determine, sorry. K into, and you have to find X. And X we already determined, that is 7.615. So that is 7.615 divided by 12, right? That is Fs into sine theta. We need to determine this theta. This theta is what? 3
Sir,
divided by 7.615. Yeah, tell me.
uh, x is deformed length or
Oh, yeah.
stretched
Sorry,
length?
sorry, sorry. X is deformed length. 7.615 minus 4, right? 7.615 minus 4. Okay? Minus mg, that is 2.5 into 32.2 equal to 0. From here, you can find k. Please calculate what is the value of k. Please tell me. Can someone tell me? I'm getting 678, 678.3. Okay, lb per feet. Okay, so this is the value of k. Now put this k into this equation. So that is from 1 from 146.958 equal to
Yes, sir.
1.2 v square plus 0.0454 into 678.3. Okay, so 46.958 minus 0.0454 into 678.3 divided by 1.25 raised to the power 0.5. You will get V equal to 3.6 feet per second. So this is the velocity. Is there any problem here? Tell me. Now, in the second part, it is asking the force exerted by the rod on the collar at point A. So, how will you proceed for this part? How will you proceed for this part? It is asking the force exerted by the rod, and that force is nothing but this normal force, right? When you resolve this Fx, when you resolve this Fs, so what is the thing here? It is N, and this
Sir,
is, yeah.
what is the question?
The question is the force exerted by the rod on the collar. I mean, definitely this rod will exert a normal reaction to the collar, and that force we need to determine. So that force is nothing but N, right? And we already got velocity and we already got Fs, then we can determine when you resolve Fs as a Fs cos theta and this normal reaction is this, then this net force is nothing but what? This net force is equal to what? Tell me, this net force is equal to what?
Fs cos theta minus n.
And equal to what? What we will write?
Centrifugal force.
Yeah, not centripetal force. Okay, so we have to determine n. N is equal to what? Fs cos theta minus mv square by r. Okay, so Fs is k times k we already got, that is 678.3 into 7.615 minus 4 divided by 12 into, now we have to write cos theta. That cos theta is that base upon hypotenuse. Base is what? 7. 7 divided by 7.615. Okay, minus m, that is 2.5 divided by r is 7, that is 7 by 12, so we will just multiply 12, 7 into 12, and we already got b, that is 3.6 raised to the power 2. Tell me, what is the value after the simplification? Yeah, I'm getting negative negative value, that is 200.96. Is that negative I'm getting?
I am getting different, sir.
What you are getting? Yeah, positive 132, right? I missed 7. You might be getting 132.3. Tell me.
131.8.
1 what?
31.8.
130. Yeah, that is same. 131.8, right?
Yes.
Yeah. So this is n. Okay. So this is conservation of energy part. Next, in the next lecture, we will talk about momentum. Momentum plus impulse. Okay. Is there any doubt?
Sir.
Yeah.
Yes. Yes, sir.
Okay. So we will discuss momentum and impulse in the
Sir.
next lecture. And yeah, is there any problem?
Yes, sir. From previous question.
Yeah. Ask.
Can we go to that question?
Yeah. 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 Sure. Yeah. Tell me.
Here, sir, at maximum velocity, the acceleration is in that direction is zero.
Yeah.
Means net force on that direction is zero.
Yeah.
So, is this statement means always valid?
It is saying that at this position only. I mean, it is asking. I mean, here there might be not the net force not be might not be zero here, but it is saying that you have to find such v such that the velocity is maximum, and velocity will be maximum when the net force in this direction is zero, because in other direction, suppose in other direction here, definitely the spring is in compression, right? In other direction the spring is in compression, and when the spring is in compression, then spring force is like this, okay, and the weight is like this. But you cannot say that this vertical component, that is fs, suppose this angle is theta, fs cos theta is balanced by this. There might be a point, I mean there might be situation where fs cos theta is greater than what, w. So for that situation there is a acceleration in this direction. Every time the acceleration is in this direction only. Every time you can see that when the spring is like this, I mean in the whole I mean at all point from this position to this position, every time the spring force is like this.
Sir,
Yeah, tell me.
No, sir. Means in between the screen was means get stuck.
Is it now good?
Yes, sir.
Yeah. So we are saying that in all position at all position in between these 2 points, always this force component is greater than this component. Then there is a definitely retardation of this collar. There is a retardation. I mean, the acceleration is always in this direction. But it is saying that suppose at this point there is no retardation. I mean, there is no net force, which means that the collar is freely moving. Okay, so at that point, definitely velocity will be maximum because the point which is earlier than this, there is a net force in this direction, and that because of that net force, there is a retardation to the collar, and if there is a retardation, then velocity will not be maximum. Are you getting my point?
Yes, sir. Means I was not asking about this. Means whenever in another if another question comes and they give maximum velocity, then is it mean that net force is zero at that point?
Yeah, yeah, that is same. I mean, suppose this I'm saying that suppose this hinged position is here. Suppose this hinged position is here. Okay, and suppose at this position spring is relaxed. So for that situation, this spring component will not come into the picture. Suppose I'm assuming that there is a situation where the spring is relaxed at this position. Suppose there is a situation where spring is relaxed at this position, which means that the whole spring potential energy has been converted into kinetic energy. So for that situation, you can easily get velocity. But here you can see that spring is not relaxed. It is in the tensile nature. So there is a definitely a spring force, which means that the spring potential energy has not been converted wholly into the kinetic energy. Okay, so that's why they have given a condition. That's why they have given a condition for that the velocity is maximum at this position. Okay,
Okay, sir.
yeah.
And sir, that force, normal force is means what is difference between centripetal? Centripetal means towards center, and centrifugal means away
No, no,
from
no, no.
center. Is it?
Centrifugal is something different. Centrifugal is something different. Centrifugal is actually a kind of pseudo force. Centripetal is force is different. Centrifugal is different. I mean the value of I mean the expression are same. Okay, but the interpretation are different. Interpretation are different. Suppose I am saying that suppose there is a situation. Okay, suppose you are doing a circular motion and you are here. You are here. I know not you are here. Yeah, you are here. Okay, and you have tied a stone by the string. You have tied a stone by the string and you are rotating. You are rotating this stone into a circular motion, into the form of circular motion. Then you will see that this stone is trying to move outward. You will see that this stone will try to move outward. But we always study that I mean that net force is nothing but a kind of centripetal force, and that centripetal force is always towards the center. But here you can see that this stone is trying to move outward. Okay, so this I mean the kind of net force for which this stone is trying to move outward, that net force is nothing but the pseudo force, and this pseudo force has the expression nothing but the mv square by r, and this force is called centrifugal force. Are you getting my point?
So pseudo force try to go means try to
I
pull
mean
that out, and centripetal try to bring
that
it.
force, that amount of force which is trying to move outward, that force is called pseudo force. And this pseudo force has the name because the pseudo force is a very general term. But in circular motion, the pseudo force is centrifugal force. Okay, because suppose you are in the elevator, okay, and you are standing here. You are standing here. Okay, now elevator is moving into downward direction. Now elevator is moving downward direction.
Then it feel light.
Yeah, then you will feel light. Okay, so how much amount you will feel light? So you will feel light because there is a force which is acting on you into the direction opposite to the this acceleration, and that force is called pseudo force. You will feel like there is a force which is acting on me, which is what? Which is moving me upward. That force is called pseudo force. Okay, pseudo force doesn't exist in nature. Pseudo force is just, I mean, there is a feeling of force. There is a feeling of force, and this force coming out from the net force. But this kind of net force always act to the directly opposite direction to the net force. This kind of force always act directly into the opposite direction to the direction of the acceleration. So that kind of force is called pseudo force. So the centrifugal force is nothing but the pseudo force, but the centripetal force is actually the net force which acts into the towards the center. So that is the difference between centripetal force and centrifugal force.
And in above example, all uh, tension, pseudo force, and centrifugal forces are equal.
Yeah, in magnitude, I mean these two are same in magnitude, but the direction are same. Direction are different because
And
this,
it
yeah.
is equal to tension.
What? This is equal to?
Tension in
Yeah, in
string.
this case it is equal to tension. I mean it depends on. I mean it depends on whether this rotation is of constant angular acceleration or not. If it is a constant angulation, then that tension force is equal to centrifugal force. That's why T equal to what? Mv square by r, and that's why this string is at the equilibrium position in this direction. Okay, but you can also see that this T is only the reason for the circular motion. You can see that centripetal force is what? Centripetal force comes because of the net force towards the center, and that is because of this tension. Still we will see that, still you will see that this stone will try to move outward, not inward. So why it is moving towards, why it is trying to move towards outward? That's why we define the word that is called pseudo force, and that pseudo force is nothing but has the magnitude of mv square by r. So that force we define for the centrifugal force. Now is it clear?
Yes.
Yeah. Is there another doubt? Okay, so we'll meet on next Thursday. Okay, and we will discuss momentum and impulse. Okay.
Okay.
Yeah. Okay, see you.
Thank you, sir.
Thank you, sir.
Yeah.